All right, time for planes in R3 in three dimensions. So we had, our standard copy of, um, we have the XY plane, right? Is kind of our standard image of a plane, right? Your x-axis, your y-axis is R2, and now there are infinitely many copies of this geometric object in R3. There's one sort of literal copy is the XY plane itself, right? Which is, we kind of um, flat, topple that over, right? Turn it down flat, and then we stick a z-axis perpendicular through it, right? Is so you have this plane itself here in R3, right? But there are going to be infinitely many more planes. And we want some way to talk about these, some way to specify them, to describe them, to work with them algebraically, right? So here's our, our XY plane down there. And if you want um, to think about representing planes in R3, um, of course, equations is one of our favorite ways to use algebra to represent geometric objects, right? So if you want to say the XY plane, right, the XY coordinate plane, there's actually a really nice way to represent that. It's the equation z equals 0, right? The XY coordinate plane, every point in that plane, what do they all have in common, right? Here's, the point -1, -2, comma 0. Here's the point, 0, comma 1, comma 0. Here's the point over here, what is that? 3, comma 3, comma 0, right? Every point in the XY plane has one thing in common, that z equals 0, right? So if you have one equation that's gonna one linear equation is going to specify a plane, right? Because you've essentially thrown out one degree of freedom from your three-dimensional space. So this is probably the easiest equation to find, easiest plane to find an equation for would be the XY plane, right? But then you can imagine finding other planes. For example, there are all these parallel copies of the XY plane, right? I could take that plane and move the whole thing up one unit. Well, that's going to be the plane z equals 1, right? And I could take that whole thing and move it up one unit, and that's going to be the plane z equals 2, right? So that's one nice family of planes that we can talk about, right? If you do z equals a constant, what is that going to be? That's always going to describe a plane parallel to the xy coordinate plane, right? At height, whatever that constant, right? Given by that constant. And then similarly for, right, very similar, if you have x equals a constant or y equals a constant, right? Except instead of being parallel to the xy plane, right? If you set x equal to a constant, say you pick all the points that have x coordinate equal to 3, right? That's now going to be 3 units removed from the yz plane, right? But parallel to the yz plane, right? And same with y equals a constant, that's going to be parallel to the xz plane, respectively. Right? So there's a nice family of planes that we can talk about, right? So this gives us any plane that's parallel to one of the coordinate planes, right? By just doing z equals a constant, x equals a constant, or y equals a constant. So this is very similar to in 2D. If you set x equal to a constant or y equal to a constant, it gives you horizontal lines and vertical lines. Same thing here, right? So you can do sort of horizontal planes and vertical planes in a certain sense, right? Um, there's certainly some that we would call vertical that aren't covered here. But at least it gives us a nice family that's analogous to the horizontal lines and vertical lines in R2. Okay, so now let's generalize this because these things they're allowed to tilt, right? So let's say, well, what if it tilts? We need some sort of more general framework. Here's the idea. We have basically two big way paradigms for representing planes. So you can do standard form of a plane. So standard form of a plane is represented as the solution set. If you do a solution set of an equation of the form ax plus by plus cz equals d, right, for constants, right, real numbers a, b, c, and d, right, so those just represent some real constants, then that solution set is going to give you a plane, right? That will always constitute a plane. And so this is one way to write the standard form of a plane. There's another way to represent this, though. So this is another form that's sometimes a little more convenient. This form, oops, then we can put 0 there. I mean, it wasn't incorrect before, but you can force the right hand side to be 0 if you do this. So you can see they're not that different from each other, and a little bit of algebra can bring you from one to the other, right? If you had they're both sort of just slight variants on standard form of the plane. The bottom form, you can imagine if you wanted to get it into the top form, you could just distribute the a through the x and through the x naught, distribute the b through the y and through the y naught, and distribute the c through the z and the z naught, and then take all the constants and subtract them over to the other side of the equation, and then the equation would look like this, right? So a little bit of algebra can morph one into the other, right? They're totally equivalent forms of a plane equation, right? Now, let's get the box back there. There we go. Then why is the second one? You might say the first one's so much prettier, right? Why is the second one preferred? Well, my claim is that there's some nice. The second one is easier to interpret, like what plane it is exactly geometrically. So this is the plane that contains the point x naught, y naught, z naught. So that's some initial point on the plane. But that has normal vector, and we'll talk about what exactly that means in a second. ABC, right? This is a normal vector to the plane. So what does normal vector mean? Normal vector means the vector that's perfectly perpendicular to the direction that the plane is going. So you can think about the xy plane, the normal vector would be pointing straight up or straight down, right? There isn't a unique normal vector. You can make it bigger, smaller. You can take its negative, right? Is still fine, So just imagine, right? If I have, the plane facing this way, then exactly to the left or to the right would be the normal direction of the plane. So, right. So any plane you have, you always have a normal vector. Well, that kind of specifies the direction of it, right? This is these coefficients, right? When you write it in this form, well, and in the other form too, right? Those coefficients give you exactly that normal direction. What's harder about this top one is it doesn't really give you a point on the plane. You can plug in some numbers for x or y and then solve for z, and you could get a point on the plane. but the second one more explicitly gives you a point, right? So that's what's nice about this one is here you have the point is sort of like staring you in the face in that equation. So um, why is this the case, right? So why does this um, have this particular point and this particular normal vector? Well, to see that this point is on the plane, that's not too bad. We said that it's a solution set, right? Um, well, pretty clearly this point is a solution to that equation, right? Because we have, if you plug in the point x naught, y naught, z naught to that equation, then you get a x naught minus x naught plus b y naught minus y naught plus c z naught minus z naught, which gives you 0 plus 0 plus 0 is 0, right? So to show that that plane contains that point is not too bad. You just plug the point in. Now, to show that it has this n as the normal vector, that's significantly more difficult, right? So here, right, we've accomplished this, right? But it's quite a bit more difficult to show that that's the normal vector to the plane, ABC, those coefficients. To accomplish this, showing ABC is the normal vector, and here normal is being used to mean perpendicular, right? You'll hear sometimes the words perpendicular, orthogonal, normal. All three of those mean the same thing. In this context, at least, they all mean 90-degree angle. That yeah. So here we have um, a key fact that we need. And the key fact is that for non-zero vectors, there's a really nice way to test and see whether or not they're perpendicular, right? If you have non-zero vectors v and w, then what can you say about them? What's the super easy test for their orthogonality? Well, if two non-zero vectors are perpendicular, if and only if their dot product is 0, right? So that's the key here. If you notice this equation, so if we use this fact to rewrite our equation, what do we have? We have, see, I have a x minus x naught plus b y minus y naught plus c z minus z naught, right? I want to, and we had that equal to 0 in our form of that equation. I'm going to rewrite this as a b c dot x minus x naught y minus y naught z minus z naught equals 0, right? These are the same equation, just written in slightly different form, right? The first one I wrote is sort of a standard equation that you would write down in algebra. The second one I rewrote using dot products, but it's the same equation, right? Because how do you compute a dot product? You take, this times this times this times this, and you add them up. Well, that's exactly what's up here, right? It's those products added up. So I noticed that equation is a dot product. Okay, that is helpful. Because then what happens next? See, now I'm going to say this means that what? This means that a point is on the plane xyz, right? So xyz is on the plane if and only if its difference from the initial point x naught, y naught, z naught is perpendicular to n, right, to ABC. Why do I say perpendicular? Well, because we said dot product equals 0, right? So that's why I can interpret that as perpendicular. Dot product equals 0 means perpendicular. So let's put a picture to this. So far, all I did was I took this equation, rewrote it as a dot product, then rewrote that using vector subtraction, and then I rewrote that in words using this fact, using the fact that dot product 0 if and only if perpendicular, right? Um, so so this here now we have the key characterization that XYZ is on the plane if and only if its difference from the initial point x naught, y naught, z naught is perpendicular to ABC. So let's illustrate this. So we're going to have x, y, z. And then I have some plane. Okay, so there we go. There's some plane floating up above our xy plane. And now here's the idea. We have some special point, some special starting point, which we call x naught, y naught, z naught. So imagine this as the tip of a vector, right? So that tip is given by this x naught, y naught, z naught, right? And now I also have some normal vector, right? And the normal vector, imagine it like this. This is our normal vector, ABC, right? So this vector forms right angles to any direction that's in the plane. Right? Now, what we're saying here is if you pick any other point, so pick some point XYZ, some generic point XYZ. How does XYZ get to be on the plane? XYZ is on the plane if and only if, so here's some other vector XYZ, right? If and only if the difference, I think we have enough colors, right? Here's the difference from, see the difference right here. Here's the difference. As long as the difference from the tip of XYZ to the tip of x naught, y naught, z naught, as long as that is perpendicular to n, right? As long as that difference, XYZ minus x naught, y naught, z naught, right? As long as that difference between those vectors is perpendicular to x to n, perpendicular to the normal vector. If this is a right angle there, then XYZ is on the plane, right? And that's if and only if, right? Imagine if I picked some x naught, y naught, z naught way up here. Now when I do that green difference, right, that's gonna be a lot less than a 90-degree angle. If I pick something above the plane. If I pick something below the plane, that's gonna be a lot more than a 90-degree angle, at least the way I have it drawn here, right? So that's the that's why this nice little form of a plane, right? This one here, right? Super nice form of a plane because it gives you the normal vector and it gives you an initial point on the plane. So there we go. So there we have a really nice characterization of a plane using a standard form equation, right? So you can describe it geometrically, probably most easily in this form, but then that little bit of algebra that we talked about before, you could toss it in this other form. Right? So that's one way that you can describe a plane. Another way that you can describe a plane is implicitly what I was doing. So you call it parametric form or vector form. It's implicitly what I was doing when I drew these gray grid lines up there in the picture above. So what you could do is you can start from your favorite starting point. So again, start from, say, that blue starting location. And then from that blue starting location, pick your two favorite directions. So pick, but directions that are in the plane, right? And directions that follow the direction of the plane itself. So pick, I'll call that, say, D1. And then pick another direction that we can call D2. I'll do that in purple also, right? And they kind of look perpendicular to each other here. They don't have to be. D1 and D2, they both have to be perpendicular to N. They don't have to be perpendicular to each other. They can be, they don't have to be. So pick D1 and D2. And then what you could do is you can write your plane this way. You can say that your plane then is going to be given by, what are the z coordinates that you find in your plane? Sorry, the points x, y, z, right, that you find in your plane. Well, they're going to be parameterized by two parameters, by s and by t. Right, so it's a kind of a parametric surface. So it's some initial point plus s times d1 plus t times d2. Right, that's another way to reach all the points in the plane. Just like to get a line, you can start from one point, pick one direction vector, and then multiply by t times that direction vector, or multiply that direction vector by t for any number t, and then add it to your initial starting point, right? Same idea here, but you need two independent parameters and two direction vectors, right? One direction will specify a line, two directions will specify a plane. So, so this is the parametric form, right, or the vector form. Now once again, just to say what this is, right? Um, S and T are free to roam over all real numbers, right? The x naught, y naught, z naught is some initial point. On the plane, right? And D1 and D2 are direction vectors of the plane. Okay. So that's another way that you can specify a plane. Now, here is an interesting question. How can we go between these, right? If you have form 1, versus form 2, right? It's not immediately clear how to get from one to the other. So here's the trick. To go, so the x naught, y naught, z naught, that's fine, right? That you can just read those numbers off in either way, in either case, right? What's a lot trickier is the ABC, right? So how can you get the ABC? Well, to get this way, note that probably the easiest way to get an ABC is by taking the cross product of your direction vectors. Because when you do the cross product of two vectors, you get a vector that's perpendicular to each of those vectors, right? And that's what the normal vector has to be. If you look up here, right, the normal vector, think of right-hand rule for cross products. Where D1 is there, put your fingertips along D1 and then curl your fingertips towards D2, and then your thumb points up in the direction of N, right? So your right-hand rule there shows you that it's a great way to get in from D1 and D2, right? So the cross product is what lets you go from those direction vectors to the normal vector. Once you have the normal vector, that's your ABC, right? Those are the coefficients. To go the other way, you have, if you want to go the other way to get direction vectors, so you have the, you already have the normal vector. Well, then you just want to find two solutions to n dot d equals 0, right? And there you have a lot of freedom, right? There are, imagine one normal vector. Well, there are infinitely many direction vectors given one normal vector, right? So you can, you just want to find two independent solutions to that equation. But you can do it by just plinking around with the numbers, right? Like almost pick anything you want for A and B and then solve for C, right? Or pick anything you want for B and C and solve for A, right? So that way is kind of easier. All right, so there's a lot of general talk about how to write down planes. Um, let's do a really concrete example. So here is the analogous example to what we did in so in the lines video. We talked about how to write lines, and then we said, okay, well, here are 2 points. Find the line, right? What's the analogous exercise here? Find 3 points. Given 3 points, find the plane that contains them, right? So 2 points specify a line, 3 points would specify a plane. So let's do this. So let's find the plane that contains, and let's pick 3 points. So let's say point A is 0, 0, 1, right? Point B, let's say is 1, 2, 4. Let's say point C is -1, -1, 1. Right? And when I say find it, what do I mean? I mean write it. Let's write it in both forms, right? In both standard form and parametric. Okay. So there's our axes. So I have 0, 0, 1. There's point A, right? 1, 2, 4. So B is up here. And then C is -1, -1, 1. So C is like back here. So there's our little, you can imagine this little triangle formed by A, B, and C, and I want the plane that contains that triangle, right? So you can imagine there's a unique plane that triangle would fit perfectly flat inside, right? So I'm looking for that plane that kind of fits our triangle there. That's a terrible try. Let's make that look a little bit better. So there we go. Beautiful? No, but conveys the idea slightly better. I think yes. So you be the judge. Let me know in the comments if the second attempt was actually any better. All right. So that's what we're searching for, right? The plane that contains this triangle, that contains these 3 points, right? As long as your 3 points aren't contained in a line, they'll specify a unique plane. Okay, so let's find this plane. So what's probably the easiest way to do it? I would start with the parametric form, because when you're given 3 points like this, you're almost handed for free your direction vectors, right? Let D1 be the difference of 2 points on that line, right? Just take B minus A to get D1. Sorry, on that, yeah, the difference of 2 points on our plane, right? So there's D1. So we'll just take their difference is 1, 2, 3, right? And then D2, for D2, we'll take C minus A, right? Just like I have drawn here. So for C2, for D2, we get -1, -1, 0. Okay. So I have my direction vectors, right? And now I need just any point to start with. Well, I'll pick A itself as my initial point. right? So there's my initial point is point A. And then from there, I'm going to add any multiple of D1 to any multiple of D2. And doing that, that's my S and the T is what those scalar multiples are. Doing that, I get every point in the plane. So that's how I can specify my plane. I can say this plane is a surface, right? Is a parameterized surface. And it's parameterized by what? By starting at the point A, and then adding S times one direction vector plus T times the other direction vector. And you could leave it like that, right? This would be a perfectly good form to leave it in. Or if you want, you can combine those into single formulas, right? So you could say this is S minus T, 2S minus T, and 1 plus 3S, right? So that triple of formulas, if you plug in all possible combinations of S and T, that will generate all the points in that plane. Great. So this is maybe an even nicer description, right? Okay, so there's our parametric form, right? So we got our vector form or the parametric form. Okay. Next, what I want to do is find my standard form, right? So to find standard form, that's what I mentioned before. The easiest thing to do is get your normal vector by taking the cross product of D1 and D2, right? This is, right, I have D1 and D2, so I want a vector that's perpendicular simultaneously to both D1, right, perpendicular to D1 and perpendicular to D2. Well, the cross product does exactly that, right? It generates a vector that's perpendicular to both of the vectors that you feed it. So that's what I can do here, right? 1, 2, 3, cross -1, -1, 0, right? So now we do our cross product. Okay, so what do we get for A? So I'm going to have 3, right? I'm just doing the standard vector cross product. 3, 3, and no, that's not right. What did I do wrong? I think that's what I need. Let's see. Is that right now? I think now that's right. Because now we have, right. So let's see, in the X component, no, we want +3. Because see, this is what I get for here. Let my failure here be a lesson to you all. Don't try to take the easy way out and get your cross product without drawing your little. So I was trying to be slick and just like do it in my head. This is why I was getting it wrong. All right, so in the X component, I need to do 2 times 0 minus 3 times -1. Okay, yeah, so that's 3. That's +3. Then, all right, what do I need next? Then I need to do the Y component. I'm going to do -3 -0. There we go. -3. There's my error. There we go. Okay, then in the Z, I'm going to do -1 minus -2. It's +1. There we go. So there's our cross product. That worked. Yeah, that worked. Now we're good. Okay. All right. Now, another thing that I should mention is why did I know right away that I was wrong before? It's because I'm, a very responsible teacher and I meticulously worked out this example before I started making this video. No, that's not why. I full this example just on the fly. I just made it up as I was going. Here's how I knew. So I want to, because this is useful, right? How did I know that was wrong? Here, this what is n? N is supposed to be perpendicular to both d1 and d2, right? So there's a quick and easy way to check that. Make sure the dot product is zero, right? That's our quick check for being perpendicular. So test that quick, right? And even though I failed to do the cross product correctly in my head, I did correctly in my head see that the dot product is not zero. So that's why I kind of paused there for a second. So test that is n dot d1, is that zero? And is n dot d2 zero, right? Make sure that those are zero. If they're not both zero, then you did it wrong. Go check your cross product, right? But even here, if you test it out, it pans out, right? This is going to be zero. And this is going to be zero, right? So this is how we know that this normal vector is valid, right? It is perpendicular to both direction vectors, and that's what we needed. Okay, so now we can write out our standard form. Right, so the standard form now is what? Well, this is ABC, right? The component of n, right? The coordinates of n, that's your ABC. So now I know what my standard form looks like. A, B, C, right? X, Y, Z. And then in here, what do I put? I put the X naught, Y naught, Z naught, right? Which in this case was our point A. And it could be any point. You could use B, you could use C, it doesn't matter. But I picked A, right? So now I'm going to put A in there, 0, 0, 1, right? So that's what we put here in our standard form. So now you can just, honestly, it's not incorrect to just leave it like this. That's a perfectly good standard form of the plane, right? You could leave it like that. But here, I mean, you'd probably clean it up a little bit here, right? You'd probably make it be 3x minus 3y plus z minus 1 equals 0. You'd probably at least put it like that, or you could even do it one better and put the 1 on the other side. Right. So again, it's not totally consistent. Some people call this standard form. Some people call that standard form. They're both fine. So, okay, there we go. So this would be a standard form of the plane containing A, B, and C, right? Containing those 3 points. So, what's a great way to check this? What was our goal? Our goal was to find a plane that A, B, and C were that contained A, B, and C. We'll check now that A, B, and C all actually satisfy that equation, right? Right? So check. We're the flight crew here. We're checking if all the registered passengers are actually on the plane before we pull away from the gate, right? So let's check, is A on the plane? So what is A? A was 0, 0, 1, which is 1. Good, right? Is B on the plane? And let's see. Oh, I forget what B was. 1, 2, 4. There we go. Okay, so B was 1, 2, 4. So let's plug in 1, 2, 4. Yep, 7 minus 6 is 1. Good. C, let's see about C. Is C still in line at Jamba Juice? Is C stuck in traffic? Or is C on the plane? -1, -1, 1. Let's see. -1, -1, 1. C made it. So there we go. All three of our points are on the plane, right? So this is really nice, right? This is there was a lot of vector operations to get to that equation, but once you have it, it's just arithmetic to verify that you actually have it correct, right? So you can check your answer very easily, in this context at least. So, okay, there we go. So there's an example of using, these forms that we developed here, right? Standard form, parametric form, and the vector geometry that connects them, to find a plane with certain given traits, right? And in this place, we specified 3 points, right? All right, cool. So let's do one more example. Let's do because there's a lot that can happen here. So let's do one more example. Let's say, for example, let's do another one. Let's find the plane containing let's say containing the line given by this parameterization as well as the point 2, 2, 2. Right, let's find this. So I have this line and this point, and I want the plane that contains them. And there will be a unique such plane as long as this point is not on the line, right? So I have 2, 2, 2, right? Somewhere up here. There's our point 2, 2, 2. And then I also have this this line. So 1, 0, 3. So I start up here at 1, 0, 3, right? And notice I'm immediately decomposing this line into an initial point and a slope, right? So 1, 0, 3 is a starting point, and then 2, 1, 0 is the direction, right? So 2 in the x, 1 in the y, and then 0 in the z. 2 in the x, 1 in the y. So something like this, right? So our line looks something like this. There's L, right? And then I want the plane that contains that point and that line, right? So you can imagine through that line L, you can pick your favorite line, right? Through a given line, there will be infinitely many planes because you could kind of put a plane on that line, then rotate it, right? So there will be infinitely many planes that contain a given line, but since we also specified a point, then there will be a unique plane that also contains that point, right? Because it's like you can rotate your plane through the line until it hits that point 2, 2, 2, and now we're done, right? Now it's locked in. So that's what I want here. Oop, um, just making it clear that that point 103 is on line L. So, all right. So let's now think about how we could do this. So, I think probably the easiest way to do it is to say if this plane that we're searching for contains this line, right? Then how can we find direction vectors? Well, one direction vector is just the direction vector of the line, right? So maybe for D1, just use the direction vector of the line. There's D1 right there, right? Because we want the plane to contain this line anyhow. And now the second direction vector, this is very similar to the previous exercise, right? Take 2, 2, 2 minus that initial point from the line 103, right? And that will get you your second direction vector. This would be 1, 2, minus 1, right? Now I have two direction vectors, right? So now I can specify my plane, right? Now I can do it. So what would my plane be? Then my plane is, it's this initial point, 103, right? That's the only point I was actually given on the plane. I mean, you could find more by plugging t-values at the L, but well, or 222, or you could use 222, either one. But I'll use 103, the initial point from y, just because that's how I kind of drew it in my picture. And then I can take as many steps as I want in the direction of D1, or as many steps as I want in the direction of D2, right? And you could leave it like this, and that's a perfectly good parameterization of that plane. Or you could combine into a single parameterization, and that's a perfectly good parameterization of the plane, right? So there we go. We did it. We found an equation of the plane that contains the given line and the given point, right? Now, if you want it in standard form, you could get it in standard form, right? I'm not going to do that here, but if you want, you could do that. How would you get it in standard form? Do what we did before, right? That would be the same process as the previous exercise. You have your D1, D2, take their cross product to get the normal vector, and then write down the standard form. So that's another thing that you could do, very similar to what we did before. So, right, same process. So here in the second example, I just showed the really new part, right? This part would be the same. All right, great. So there we go. Different ways to write planes and a few exercises of looking for planes that have some given properties. Thanks.